Welcome to Statistical Quality Control. Today we are diving into acceptance sampling plans. Imagine you are a quality inspector at a massive manufacturing plant. Thousands of items are rolling off the assembly line every hour. How do you ensure quality without inspecting every single piece, which would take forever and cost a fortune? That is exactly the problem we will solve today. Let us get started. To understand why we need this, imagine you are buying a massive truckload of apples to make cider. You cannot possibly bite into every single apple to check if it is sweet, because then you would have no apples left to sell. Instead, you pull out a small basket, test those few, and make a decision about the whole truck. In factories, 100% inspection is often impossible, destructive, or simply too expensive. Acceptance sampling is the practical statistical shortcut that saves time and money while still maintaining high-quality standards. Now that we understand the intuition, let us look at how a formal plan actually works. An acceptance sampling plan is a specific statistical rule used to decide whether to accept or reject a large batch of products, which we call a lot. The plan relies on two crucial numbers. First is the sample size, denoted by N. Second is the maximum allowed number of defective items, denoted by C. The rule is simple. If the number of defectives in your sample is less than or equal to C, the entire lot is accepted. If it strictly exceeds C, the lot is rejected. Because we are only looking at a small sample and not the whole lot, we are essentially making an educated guess. And guesses can sometimes be wrong. Think of a smoke detector. Sometimes it goes off from burnt toast, which is annoying but safe. Other times it might fail to detect a real fire, which is dangerous. In manufacturing, we face two similar errors. The producer's risk, denoted by alpha, is the probability that a perfectly good lot is accidentally rejected. The consumer's risk, denoted by beta, is the danger that a terrible, highly defective lot is accidentally accepted. To calculate these risks, we must define what makes a lot good or bad. This brings us to AQL and LTPD. The acceptable quality level, or AQL, is the baseline percentage of defects that the consumer considers completely acceptable. The producer's risk is evaluated exactly at this AQL. On the flip side, the lot tolerance percent defective, or LTPD, is the absolute worst case defect rate the consumer is willing to tolerate. The consumer's risk is evaluated at this LTPD. These two benchmarks allow us to mathematically balance the fairness of the sampling plan for both the buyer and the seller. To calculate the exact probabilities of these risks, we need a mathematical model. When the lot size is very large and the probability of a single item being defective is very small, we use the Poisson distribution. This formula predicts the exact mathematical odds of finding a specific number of broken items in our sample. Let us break down the symbols. The letter E is Euler's constant. The variable N is our sample size, and P is the true fraction of defective items in the lot. Multiplying them gives N times P, which is the expected average number of defectives. Finally, D is the specific number of defectives we are testing for. As the true defect rate P increases, the chance of finding zero defectives drops rapidly. Now that we have the formula for exactly one outcome, how do we find the total probability of acceptance, denoted as PA? We must add up the individual probabilities of all acceptable outcomes. If our maximum allowed defectives is C, we calculate the chance of finding exactly 0 defectives, exactly 1, and so on, all the way up to C. The large sigma symbol represents this summation. We calculate the Poisson formula for every single acceptable outcome and combine them into one final percentage. If the lot quality gets worse, meaning P increases, this total probability of acceptance will drop significantly. This brings us to the operating characteristic curve, which visually summarizes everything we just discussed. Look at the horizontal axis, which represents the true lot fraction defective. The vertical axis shows the probability of acceptance. Notice how the curve starts high and drops as the lot quality gets worse. At the top left, you can clearly see the producer's risk, alpha, evaluated at the acceptable quality level. At the bottom right, we see the consumer's risk, beta, evaluated at the lot tolerance percent defective. This curve is the ultimate tool for evaluating if a sampling plan is fair to both parties. Let us see this with a concrete example. A factory produces light bulbs. The inspector tests a sample of 50 bulbs, so N equals 50. The shipment is accepted if they find one or fewer defective bulbs, meaning C equals 1. If the true defect rate of the shipment is 2% or P equals 0.02, what is the probability of acceptance? First, we must find the expected number of defectives, N times P. Multiplying 50 by 0.02 gives us exactly 1.0. This means, on average, we expect to find exactly one defective bulb in our sample. Continuing with our expected average of 1.0, we must now calculate the probability of finding exactly 0 defectives and exactly 1 defective. For 0 defectives, we plug D equals 0 into our Poisson formula. Any number to the power of 0 is 1, and 0 factorial is 1, leaving us with e to the power of negative 1, which is approximately 0.3679. Next, we do the same for exactly 1 defective. Plugging in D equals 1, the math is just as clean, and we again get 0.3679. 0 and 1 are equally likely here because our expected average was exactly 1. To find the final probability of acceptance, we simply add the acceptable outcomes together. We take the chance of finding 0 defectives and add it to the chance of finding 1 defective. Adding 0.3679 to itself gives us 0.7358. This means there is a 73.58% chance the inspector will accept this shipment, even though 2% of the bulbs are actually defective. This shows that this specific sampling plan is relatively forgiving. Now, let us look at a second example, using the exact same sampling plan, where N is 50 and C is 1. This time, the manufacturer and buyer agree that the acceptable quality level is a defect rate of 1%, so P equals 0.01. We want to find the producer's risk, alpha. First, we must find the probability of accepting this good lot. We calculate our new expected average, N times P, which is 50 times 0.01, giving us 0.5. Because the lot quality is better, our expected number of defectives has dropped to half a bulb. Continuing our calculation, we set up the sum of the Poisson probabilities for D equals 0 and D equals 1, using our new expected value of 0.5. The first fraction simplifies to just the exponential term, e to the negative 0.5. The second fraction leaves a 0.5 multiplier. Factoring out the common exponential part, we get 1.5 times e to the negative 0.5. This evaluates to 0.9098. So there is a nearly 91% chance that this perfectly good lot will pass the inspection. We have the probability of acceptance, but we are looking for the producer's risk, which is the probability of rejection. Since a lot must either be accepted or rejected, these two probabilities add up to 1. Therefore, the risk of rejection, alpha, is simply 1 minus the probability of acceptance. Subtracting 0.9098 from 1 gives us exactly 0.0902. This means there is a 9.02% chance that a perfectly acceptable shipment will be unfairly rejected just due to bad luck in the random sample. We have covered a lot of ground today, so let us summarize the key takeaways. First, acceptance sampling is a practical statistical method that balances the cost of inspection against the risk of passing bad products. Second, we use the Poisson distribution to mathematically model the probability of accepting a lot based on sample size and defect rates. Finally, the operating characteristic curve visually demonstrates how a plan balances the producer's risk against the consumer's risk. You now understand the mathematical backbone of global manufacturing and supply chain logistics. Great job!